Good, so it seems to work. Well, it's a great pleasure that Peter Müller from LMU Munich is giving a talk today in our seminar on entanglement entropy for quasi-free Fermi gases. So looking forward to your talk.
Yes, thank you, Felix. Thanks for the invitation to give a talk in your seminar series. And hello to everybody in the audience. You may have noticed that I have slightly changed the title of the talk. This does not mean that you are going to hear a totally different talk. It's just that I try to focus a little bit more on a review talk instead of going too much into detail with one specific topic. And I thought that this changed title would be more appropriate in that case. So no panic.
That sounds very good.
And I should not forget to say, if you have any remarks or questions, I mean, please don't feed the chat because probably I won't be able to see it. So just interrupt me and speak up. Good. So yes, title entanglement entropy for quasi-free Fermi gases. And first I should clarify some words in the title. I have two introductory slides, which are a bit more on the physics background that should motivate what we will be looking at for quasi-free Fermi gases. So if you're not into this, I ask for your patience, and then you can get back, if you're just interested in mathematical issues, get back on the third slide where everything will be defined properly and you won't have lost anything. So what is entanglement? If you look at a composite quantum system, and what I have in mind from the very beginning is a quantum system of two parts, like here in this example down there with two Hilbert spaces HA and HB. And if such a system is prepared in a non-product state, then one says that the system is entangled. And the consequence of this is that if you do experiments on that systems, you will be able to detect non-classical correlations between the two subsystems of the composite systems. And these correlations, they are a key feature of quantum mechanics. So they wouldn't appear in any classical, in a classical theory. And they were already discovered quite early in the history of quantum mechanics. In fact, it was Einstein in the mid-30s who got very much worried about spooky actions at a distance. And then it took quite some while, and then, well, 29 years later, after the first paper by Einstein, Podolsky, and Rosen, the works of Bell clarified that entanglement rules out interpretations of quantum mechanics that are both local and realistic at the same time. But entanglement is not only of interest for academic or for academic questions, it is also relevant for modern technology based on quantum features, namely specifically quantum issues of quantum communications and quantum computing. So it is clearly desirable that one has some kind of measure, some should say quantifier of entanglement. And in fact, there are several such quantifiers around. Here in this talk, I will concentrate on the von Neumann entropy. Just to mention, the von Neumann entropies can be generalized to Rényi entropies, then there is the logarithmic negativity and others, but here we just focus on the von Neumann entropy. So to be a little bit more concrete, let's suppose that the product, this composite system that consists of two subsystems A and B with the corresponding Hilbert spaces, that this is prepared in a pure state psi, so that the corresponding density operator, this you see, that's the rank 1 projections, pure state. Now, I am interested in forgetting all the information that pertains to subsystem B, which is contained in rho. And one way to do so is to take the partial trace of rho with respect to the Hilbert space HB, which means what you're left with is an operator on the Hilbert space HA alone. And this is, again, a density operator. We say the reduced density operator now on the subsystem A. Well, the point here is that if psi is not a product state with respect to this decomposition here, then this reduced density operator rho A is not a pure state either. So it's a mixed state, even though we started with a pure state here. And that's, for example, that's totally different in quantum mechanics as compared to classical mechanics, because in classical mechanics, reduced states of pure states are pure. And so this is a mixed state. It has eigenvalues between 0 and 1, and which sum up to 1. And in order to measure the entanglement, we want to measure, in quotation marks, the degree of mixedness of this reduced density operator. And one way to do so is to think of the eigenvalues of rho A as a classical probability distribution and look at this at the classical von Neumann entropy of this probability distribution. And this is precisely what is done here. So we take this reduced density operator on the Hilbert space, which is now only an operator on HA, and this is not a partial trace here anymore. This just symbolizes that the HA Hilbert space is also traced out now, so we are left with a number. And so if you were to compute the trace in the eigenbasis, this would be the von Neumann, the classical von Neumann entropy of this the distribution of the eigenvalues of rho A. And this quantity here, that is called the entanglement, or the von Neumann entanglement entropy of the state psi with respect to the subsystem A. It's just to make it clear, well, the function that we have here, the minus lambda logarithm lambda, and the logarithm here is a binary logarithm, but that's not the crucial point. If I just draw it, then it looks like this. So here is 1, here is 0. And you see, if we were to put in a pure state psi, a rank 1 projection into the von Neumann entropy, then because this function vanishes at 0 and at 1, it would be 0. So being positive, this means that the entropy pertains to a mixed state, and the larger it is, the more the mixedness and the more the entanglement. That's the intuition. Good. From now on, I will be interested, because there is Fermi gas in the title. I will be interested in many body systems. First of all, they can still have interactions. Later on, no. And I will be interested in the ground state of such a many-body system. Well, you may say, if I think of the free Fermi gas, in RD, this doesn't have a ground state, well, because it's translation invariant. So in order to have a well-defined ground space, to be on the good side, let us restrict this many-body system to a really large region gamma. If we are in the continuum in RD, I will also look at discrete systems, then we're in ZD. And then this many-body system is described by the Fock space over the single particle Hilbert space with respect to gamma. Okay, now we want to do the very same thing that we did before. We look at the corresponding pure state, psi, and we want to, in this density operator, we want to forget some of the information of this quantum system. And so what was the subsystem A before? This is now a subset lambda in space. And I want to forget all the information that is in this density operator that comes from the complement gamma without lambda. So what I do is I trace out the Fock space over the single particle Hilbert space referring to the complement of lambda. And in this way, I get a reduced density operator, and then I look at the von Neumann entropy of this reduced density operator. Well, precisely what we had before. Good. Now, of course, it's a bit cumbersome to have systems being restricted to some artificial large volume. So this is a good opportunity here to get rid of this finite volume now after everything, the trace has been taken. And when I formally, so I think of a macroscopic limit here, meaning volume to infinity, number of particles to infinity, having a well-defined density. Good. Okay. If you think of statistical mechanics, then you're used to entropies being extensive quantities, so they grow with the volume of the system. This is not always true for entanglement entropies. And in fact, it was Bekenstein in 1973. I mean, he analyzed toy models for black holes, and he found that the kind of entropies he looked at for in these toy models, they didn't grow with the volume, they grew only with the surface area. And that caused a big surprise and an enormous amount of interest in such kind of entropies. And nowadays one can say the following, namely, typically, if you look at a quantum system and the state, and the state in which it's prepared is the ground state, then there is typically an area law. That means this is what Bekenstein found. So if I scale up the volume lambda here by a factor L, so I make it larger and larger, then the entanglement entropy grows with the surface, or it grows a little bit faster. There is an additional logarithm, and this is often referred to as an enhanced area law. Okay, so typically area laws here, they can be found in situations where the many-body system displays or exhibits a gap above the ground state. The gap can be a spectral gap. It could also be a mobility gap. But whenever this is true, the ground state is in a way separated from the excited states. You should expect an area law. Otherwise, you should expect an enhanced area law. Good. It's clear that these different types of behavior, whether there is a gap above the ground state or even only a mobility gap or no, that this has triggered an enormous amount of interest in people who study disordered many-body systems, where the so-called many-body localized phase is still a great mysterium, and one is eager to have signifiers that might indicate whether there is a localized phase or not in these interacting many-body phases. But I would like to emphasize that even in such seemingly trivial quantum systems like quasi-free Fermi gases, meaning I have no interactions between the fermions, the only thing, but the fermions can be in a background potential. This is what I mean by quasi-free. But even in these really simple situations, the entanglement entropy and its analysis is non-trivial. It gives rise to mathematically very challenging questions. And I just saw that you had Wolfgang Spitzer give a talk in December in your seminar. So if you remember some things he did, I mean that's what I'm referring to here, because that relies on this analysis relies on deep mathematics. I'm going to mention later on. Okay, so From now on, I'm interested in quasi-free Fermi gases, and this means I have to look at their ground state. Their ground state of a Fermi gas is a Slater determinant, so it's a totally anti-symmetrized product of single particle eigenstates, and I have to take the lowest single particle eigenstates. So these are the eigenstates. This is the single particle operator. This is the corresponding eigenvalue. Well, how many of these do I have to take? Well, this depends on the density of the gas. The bigger the density, the bigger the so-called, or the higher the so-called Fermi energy EF. There's a one-to-one relation between density and particle density of the gas and Fermi energy. And so the density of the gas is encoded in the Fermi energy, and I have to take here totally anti-symmetrized products up to the Fermi energy. Good. So that's in a way the end of this more physical part, and now I will just I will get back to a more mathematical setting. But before, let me say, since in a quasi-free Fermi gas there are no interactions, it is clear that this whole procedure that one has to do here in order to compute the entanglement entropy, this procedure can be carried out entirely in the single particle Hilbert space, because of absence of interactions. And in fact, it's an exercise to compute what you have to do in order, what you have to do on the single particle Hilbert space to compute this entanglement entropy. I have summarized the results for this entanglement entropy of the ground state, referring to the ground state with Fermi energy EF in this lemma, but since I'm not showing it to you, you may simply, and that's the start of what you say of the mathematical part, you can take this as a definition here of what we are going to look at, and I will explain it in detail. So we have a single particle Hamiltonian, typically a Schrödinger operator, magnetic Schrödinger operator, either in the continuum or discrete. Then the Fermi energy, that's a real number. And we are interested in a subvolume of RD or ZD, okay? And now this procedure of computing the entanglement entropy amounts to the following. You look at the so-called Fermi projection of the Schrödinger operator, the Hamiltonian. That's the spectral projection of H associated with the interval from -infinity up to, and that's my convention, but excluding the Fermi energy EF. So that's just, as I said, that's shorthand for -infinity to EF. Okay. Good. And okay, that's the spectral projection. Then the spectral projection is truncated. It's truncated by indicator functions referring to this subvolume lambda. And of course here, these indicator functions, they act as multiplication operators by the indicator function. Then that's a nice operator. I take a function h of this operator. This function h, if it was just this part here, then this would be the function that you know now from the von Neumann entropy. But in fact, in this single particle, effective single particle description, the function h is more, I mean, the function you have to look at here is more complicated. It has an additional term. And just to motivate the additional term, that is due to the particle hole symmetry of the many particle system, because you see that symmetry here when lambda is replaced by 1 minus lambda, particles and holes. Good. So that's an operator on the single particle space, and we take the trace. Okay. And since here, there's a binary logarithm, and I have the convention that 0 are not only the natural but logarithm, but also the binary logarithm. So the same applies to log 2 is always 0. Okay. Let me briefly sketch the function h to be a little bit more concrete. So we have, this is lambda. Here's 0, here is 1. The binary logarithm at 1/2 is -1. So here is 1/2. Everything is symmetric with respect to 1/2, and the function h looks like this. It has infinite slope near 0 and near 1. Okay, so this is h of lambda. That's what it looks like. Okay, and the fact that the slope is infinite here, this is one complication. One complication why analyzing entanglement entropies is non-trivial. The other complication, which is more severe, is that the so-called symbol, that's the function of the operator we take here, that this function, this indicator function, is apparently not smooth. It has a discontinuity. That's the second complication that makes the analysis of entanglement entropies complicated. Okay, so you may take this as a definition of what we are looking at. And now I'm going to show you a sequence of theorems of what people know about entanglement entropies and whether they, for such quasi-free Fermi gases, and whether the entanglement entropy displays an area law or an enhanced area law. Okay, so we start with the most simple quasi-free Fermi gas, with a free Fermi gas. So here, the single particle operator is simply the negative Laplacian, the free operator. For things to be interesting, I want a Fermi energy, of course, in the spectrum, so it has to be positive. And this results, this is true, this is due to Leszke, Sobolev, and Spitzer. We look at the entanglement entropy of a scaled up domain. So lambda here is a bounded Lipschitz domain. This means, well, it's bounded, it's open, it's connected, and locally it can be represented as lying above the graph of a Lipschitz function. So that's what's contained in here. And in addition, the boundary should be piecewise even smooth. So it allows, for example, for cubes. I like cubes. Good. And but that's this condition on the boundary is only needed if the dimension is at least 2, because in 1 dimension boundaries are not very complicated, as you know. Good. Then the statement is that there exists a constant, and this constant in quotation mark, this constant, well, it depends on the Fermi energy, it depends on the space dimension, and it depends only linearly on the surface area of the unscaled volume lambda, such that when we make L larger and larger, so asymptotically, when L tends to infinity, you see there is an enhanced area law, so surface times logarithm, and this multiplied by a constant. So this is the constant of the asymptotics. And the rest are subleading terms. One cannot say more than just little o of what you have here. Okay? That's from 2014. I comment on it in a second. Before, let me mention the second type of result that is very similar. It's due to Pfirsch and Sobolev from 2018, this time in 1 dimension. And the gas is not free anymore, but quasi-free. So we have a background potential. In this case, the background potential is smooth, arbitrarily often differentiable. And that's the crucial thing, it's periodic. So that's a periodic Schrödinger operator. And the Fermi energy is supposed to lie in the interior of the bands of this periodic Schrödinger operator. The result is the same asymptotic still holds true, in particular with the very same constant sigma 0. This means, what I would like to stress, since the constant was derived for the free system, the constant does not depend on the periodic potential. It's independent of the periodic potential. Okay. So some comments. So if I want to use sophisticated words, I should say that these two results, they represent as Szegő type asymptotics for truncated Wiener-Hopf operators with discontinuous symbols. So just to explain this a little bit, in the early 50s, Szegő analyzed the determinant of large truncated Toeplitz matrices. Now, if you think that the determinant, so det M of a matrix is equal to e to the trace logarithm of the matrix, okay, so there is already a connection because there is the trace of a function of the matrix. And the matrix in Szegő's case was a truncated Toeplitz matrix. Well, here we don't have a truncated Toeplitz matrix. Here we have this operator, that's this spectral projection truncated by the indicator functions to the volume lambda. And this is what is in the continuum setting referred to as a Wiener-Hopf operator. So this is why I said Szegő type asymptotics for truncated Wiener-Hopf operators, and they said that the symbol here is discontinuous. Now that is the symbol. Good. So this explains the jargon here. Well, the proof of both of these results here, this proof relies on Widden's formula. That's a formula Widden set up in a one-dimensional context in the 1980s, and it was generalized in 2 years later, again by Widden, to apply to more general operators, but that was unclear. It was unclear until Alex Sobolev, in a series of really high-level papers using the machinery of pseudo-differential operators, proved this generalization of the Widden formula. And with this Widden formula, one can then obtain these these asymptotics here. Okay, so that's just in buzzwords what goes into it. I should not forget to say that there are, of course, precursors of this type of results in the physics literature by Joff and Klitsch and by Wolf for discrete systems. And so, I mean, the result is the same here. So you can ask, I mean, what is responsible for it? Well, one common feature is, of course, that both the free Laplacian and the periodic Schrödinger operator, they have only absolutely continuous spectrum. So that's in a way that should account at least for the enhanced area law in both cases, but it's by no means meant as an explanation why the constant here is the same constant as here. Okay. I should not forget either to say that the results in these two papers here and here, they are more general than what I've written down here. They do not only apply to the function h, this function a, this function h we have here, that I drew here, but they apply to a much wider class of functions. These functions are called test functions in this business. And the generality they allow for is piecewise continuous, Hölder continuous at the right at 0, and Hölder continuous from the left at 1. That's yes, that's what is needed. Yes. Okay, so here a special case, and the entropy function h, little h, from the previous slide that does the job, because I mean, this is here only a logarithmic derivative, logarithmic singularity in the derivative, and therefore we are held a continuous. Good. So that's these are instances for enhanced area laws. Then there are, and I'm telling you all that is known about it, because I mean there is no general theory for the behavior of entanglement entropies. There are just some systems known, some Schrödinger operators known, for which the behavior has been obtained in a more or less cumbersome way. So then we will say what we can say today. Good. The next, this slide is about area laws. So no logarithm anymore in the asymptotics, just a surface. And the first results, again by the crew Leschke, Sobolev, and Spitzer, is for the Landau Hamiltonian in 2 dimensions. So the Landau Hamiltonian, that's the magnetic Schrödinger operator in 2 space dimensions with a constant magnetic field. So this is here, I've written down the vector potential for the constant magnetic field B in symmetric gauge. The gauge doesn't matter, of course. Yes, and that's the Schrödinger operator we're interested in. This Schrödinger operator, the Landau operator, has only a pure point spectrum. The eigenvalues are called the Landau energies or Landau levels, and they are given here. So that's the sequence of the Landau levels. They are proportional to the magnetic field. And I didn't say b larger than 0 here. I should say b larger than 0. Otherwise, I should have absolute values here and there. Good. So these are the Landau levels at odd multiples of b. And what we do is, okay, the region lambda that will be scaled up by L, again, it has to be nice. It has to be a bounded C3 region this time. And clearly it's a subset of R2. We scale it up, and then the result is the entanglement entropy grows with the surface. Well, we're in 2 dimensions, so the surface is linear growth in there. And then there's subleading terms little of L. Since there is the dependence on B is interesting, I have singled it out from the constant here. So it grows with square root of B. And I've also singled out the dependence of the boundary of the unscaled volume lambda. That's also a linear dependence. And the rest, the psi n here, that's simply a numerical constant. Okay, so this is an example of an area law.
Wolfgang Spitzer mentioned this result at the end of his talk. So he explained us precisely this result.
Very good. So just it's, and I mention it because it's for filled Landau levels. If one had a way in order to say, or if it's not, no, one would expect something different if the Landau level was not totally filled, if it was only partially filled.
It makes sense because then there's no gap.
Yeah, yeah. Exactly. No, you know, I mean, the Landau levels the Landau level is an infinite degenerate eigenspace, and so there would be ample space for excitations, and these excitations, this is what one would expect, should give rise to the enhancement with a logarithm. The second result that gives an area law also refers to an example where there are no excitations possible that may in a way lead to some kind of dynamic that may lead to transport, and that's in the context of Anderson localization. I'm not going to explain this, just giving you so no, there is no knowledge of Anderson localization required here. Let me just briefly say what it's about. So this time we have a discrete Schrödinger operators in d dimensions. So on the d, lambda L is a cube this time, so discrete cube. The operator is random, and its realizations act like this. So psi is a function from little L2, and I evaluate this as a point x in ZD. Then I have here the discrete Laplacian. So this Laplacian is the discrete Laplacian, nothing fancy. And then I have a potential sitting at each point of the lattice ZD. And these V omega of x, these are realizations of independent and identically distributed random variables. That's all. They can be bounded, they can be unbounded, I don't care. But just to keep everything simple, and because I write down a theorem, there should be an absolutely continuous probability distribution of all of these random variables. Good. Now, for such type of operators, there is a subset of the spectrum which is called the region of complete localization. And this subset of the spectrum has a peculiar feature. First of all, it's a dense pure point spectrum. Secondly, the corresponding eigenfunctions decay exponentially. And third, there is no kind of transport possible in the sense that if you prepare your system in as corresponding eigenstate to a spectral value here in this region, in this spectral region, and you time evolve this state, and you look at any moment, the moment can be as high as you like, any spatial moment of the time evolved state, then this spatial moment remains bounded in time. So this is what people would call dynamical localization. And a state that is originally located somewhere does not get lost to infinity somewhere. Okay, and we take our Fermi energy as lying inside this region. Then the statement of Pastur-Slavin and Elgar Pastur-Scherbina is that if you take the expectation value of the entanglement entropy, you make L again, you divide by the surface, you make L large, you have a limit. So that's an area law, because it grows like a surface. Now you have, basically, you know everything, all the systems for which the entanglement entropy has been analyzed from a mathematical, rigorous point of view for quasi-free Fermi gases. Quasi-free Fermi gases. And you may ask, so what actually determines whether there's an area law or there is an enhanced area law? So one question, of course, I mean, I try to hint at it already a little bit, is of course, well, there is on the one side, there is absolutely continuous spectrum and delocalized states like plane waves, where you have an enhanced area law. On the other hand, you have this filled Landau level here, and you have these exponentially decaying eigenfunctions here, where there is an area law. And so in a way, the question is natural. What really determines, I mean, how good must localization be in order to have an area law and not an enhanced area law? I'm coming back to this later, to this question, but before, I would like to stay in the realm of enhanced area laws and mention the topic that was originally the title, namely stability of enhanced area laws, because that adds another, in a way, another hint to what is going on. Good. So this we do now. And stability here refers to stability of the enhanced area law of the free Fermi gas. So this is what Leszke, Sobolev, and Spitzer did in 2014 with a constant sigma 0 that was the same constant as in the periodic case of Fiersch and Sobolev. And the statement is this. So since we reduce it, I mean, we reduce it to what Leszke, Sobolev, Spitzer did, we need the same kind of assumption on the domain. unscaled domain lambda. That's the same as before. In addition, we want that the origin lies in the interior of lambda. I mean, that's not a big deal. Okay, then we have a potential. We look at this Schrödinger operator, minus Laplacian plus the potential. We are in the continuum. The potential is bounded, that small is for simplicity, but that simplifies analysis a lot, namely that the potential is compactly supported. So if you wish, we are in a very nice scattering, situation here. We have a compactly supported bounded potential. And it's also clear that the spectrum is the non-negative half-line. And we look at Fermi, the essential spectrum is the non-negative half-line. There may be eigenvalues lying below, but only a finite number. And I take the Fermi energy in the absolutely continuous spectrum. Then the statement is, there are two constants, and one constant bounds the lim inf of the entanglement entropy when scaled up by L and divided by the length dependence of the enhanced area law, and the other constant bounds from above the lim sup. So this means that the entanglement entropy, because these constants are non-negative, that the in particular this constant is non-negative. Sorry, this constant is strictly positive. That's what I want. Since this is strictly positive, so this means that the entanglement entropy grows at least as surface times logarithm. And the other inequality, because sigma u is finite, says it grows at most like logarithm, surface times logarithm. And so we can also say something about the constants. The lower constant is smaller than the unperturbed constant from Leszke, Sobolev, and Spitzer that also showed up in Firsch and Sobolev for the periodic potential, because this factor, well, pi squared is 10, so this factor here is smaller than 1. And well, the upper constant seems to be larger than sigma 0. There is nothing, I don't know whether 1672 was a special year in the history of mankind, but there is no significance to this number. I didn't write down the expression in one dimension, because in one dimension, we were only able to derive a potential dependent constant, which is not something we believe in. I mean, it comes out of the proof, but that's not something we believe in, because we know that Firsch-Sobolev, who are also in one dimension and had the periodic potential, did not have had the same constant as for the free Fermi gas. Okay. So, but message is again, there is something like an enhanced area law here. And again, of course, I said that we have absolutely continuous spectrum on the non-negative half-line. There is, I mean, if the potential is sufficiently negative, is allowed, then there may be eigenvalues below the onset of the AC spectrum. But due to the fact that the potential is finite and has compact support, there can be at most finitely many eigenvalues on the negative half-axis. And therefore, if there are only finitely many eigenvalues, say, okay, here is an eigenvalue. And here is my Fermi function. That's this indicator function that defines the symbol. Okay. What I can do is, since this eigenvalue is isolated, well, from the left, I can smooth out this Fermi function here. But this will not affect the operator, because the operator has no spectrum there where I changed the function. So but on the other hand, for smooth functions of Fermi projections, one knows that these functions, they have a good decay, maybe a good polynomial decay. And then one can use this polynomial decay to show that the entanglement entropy grows at most like the surface. So since there may be spectrum at negative energies, it's of course, one can ask what happens at these negative eigenvalues. Answer at most an area.
Just a stupid question, Peter, to this point. Is it correct that in this case only a finite number of particles are occupied and a finite number of states are occupied? If this EF is negative.
If the EF is negative, then I have only a finite number of states occupied. Yes, that's true. So you can say it's not a big surprise.
And don't these wave functions also decay at infinity, say exponentially or something?
Yes, they should decay exponentially. Yes. So I'm not saying that this is something something spectacular. This is why I did not mention it in the theorem, but only as a remark down there. I mean, it's not surprising. I wanted to say there is also a technical reason why one should not expect more than a surface growth.
Well, my question maybe is even more naive. I mean,
it's totally it's not naive.
All decay exponentially, then I would just expect it to get zero if you make the volume big enough, because basically near the boundary everything is zero. Or is this
because there are only finitely many. This should be. I have the projection. No, this is not clear. It's actually not. This is not clear to me. Let me go back. No, that was. Let me go. So you have so this is a finite dimensional projection.
Mm-hmm.
This is a finite dimensional projection. Then you truncate it, and then you take this function. And I'm not so it's not clear to me why the result should be zero. The point is that the truncation does not commute with the projection.
But if things decay exponentially fast, and basically this projection
that's not you get something that should not grow fast.
Okay, I see that my picture was a bit too naive. I understand this.
It's not zero, but I think your point is that one should expect something even slower than a slower growth than L. Could be even constant.
Mm-hmm.
It cannot be zero, but it could be constant.
And this could happen. So your result just shows it grows at most at this rate, but it could even grow slower.
Yes, here we show that's at most. That's capital O.
Mm-hmm. Okay.
Whereas in the AC spectrum, we have this positive constant.
There's also a lower bound, sure.
Yeah. So that's the point. I would also like to advertise that we are more or less done now with an improvement of the theorem here. Namely, we can show that the two constants sigma L and sigma U, they coincide, and they are equal to the constant sigma 0 from Leszke, Sobolev, and Spitzer. So we are in the same situation that for this bounded and compactly supported potential, the asymptotics, because then we have, since everything coincides, we get the asymptotics here, the leading term of the asymptotics. The constant of this asymptotics does not depend on the potential. And we can also extend it to more general test functions, so it's not only valid for the entropy function, but it's more or less the same class than the Segu people always looked at. So that was in a way too new that I dared to put it as a theorem. Okay. If there are no further questions, I would like to come back to this question that how much delocalization is actually needed to get an enhancement, or how good, put it in another way, how good must localization be to have an area law and to avoid the enhancement. And so we've seen different situations now, and to shed light on this question, we look again at a random model, this time a one-dimensional random model. And I will, so first I explain the model that's here. Then I will tell you why this model is interesting. I mean, we didn't look at this by chance. And then I tell you the results. Okay, so this is a one-dimensional discrete model. So this is the discrete line. And again, we look at an Anderson type operator. So we have here the discrete Laplacian in one dimension, or the discrete adjacency operator, depends on what you like to call Laplacian or adjacency. And then there is a potential at every site. This point, this time, on the one hand, there is a coupling constant, that's my disorder strength. And then there's a random variable associated to each point in ZD in such a way that, say, this is the origin of ZD, here is -1, here is +1, then two neighboring sites always share the same random variable. So at site 0 and at site 1, we have the same random variable. At site 2 and at site 3, we also have the same random variable. That's this condition here. Apart from that, so this random variable is independent from that random variable, is independent from the random variable we have at this pair here, and so on. So again, independent and identically distributed random variables, except that always two sites have this, two neighboring sites have the same random variable. And another thing that is different from before, the probability distribution of these random variables here is now a very special one. It's a Bernoulli distribution, namely with probability p, the random variable is 0, and with probability 1 minus p, it's 1. So only two values available, either 0 or 1, which means that the discrete Laplacian here gets a potential either by sees a potential of 0 or of little v, when capital V is 1. Okay, this gives rise to that spectrum here. So this is the spectrum of this operator H omega, and it's actually the same spectrum for almost every realization H omega. Just believe me. And it looks like this. Well, it has a simple structure. If all the random, if here V is 0, there is no potential. So then you just have the spectrum of the adjacency operator. That's the blue interval here, from -2 to +2. Well, if you think for a moment, all the random variables were 1, then the spectrum would be shifted by V. So that's the red interval here, from -2 +V up to 2 +V. So simply this is the Laplacian spectrum shifted by +V. And the union of the blue and the red interval, that's the whole spectrum. Okay. And I have drawn here two energies in the spectrum in green, namely 0 and V, because these two energies are special, as you're going to see now. I tell you the results. So first of all, there is a result about localization, namely, whenever you take an interval I, that is I, compact in the spectrum, and it does not touch 0 or V. So for example, I is here. This is I, or this could be I, or this could be I. Yeah? But this is not allowed for I. Okay, so if I stays away from 0 and V, then the statement is there is only pure point spectrum, dense pure point spectrum in I, and the corresponding eigenfunctions decay exponentially. So in the same thing as I told you before, except that the decay, how fast your eigenfunctions decay, this decay length gets worse and worse. It gets larger and larger when you approach these two green critical energies. But still, the spectrum as a whole is almost is a pure point spectrum, nothing else. Good. Yet, if you prepare your system, say, at the origin, so at time 0, your system is at the origin. Then you time evolve it, yes, with this operator, you time evolve it, and you multiply by the position operator and take the Hilbert space norm. That's the second moment of the time. I mean, this norm, Hilbert space norm, is the second moment of the time evolved state. So if it grows linearly with t, this would be diffusion. If it grew like t squared, this would be ballistic. And you find, and this is this is the physicists Dunlap, Wu, and Phillips, and it was proved by Zhytomyrskaya, Schulz, Baldes, and Stolz, that this second moment grows super diffusively, more than diffusive. And this is an indication of a dynamical delocalization. And this dynamical delocalization is due to the worse and worse decay of the eigenfunctions the closer you get to these two critical energies. So it's a fact. I mean, I'm telling you the results of a couple of theorems. Now you can imagine what we are interested in. What we do is we put our Fermi energy precisely at one of these critical energies and see what happens. And surprise, it's an enhanced area. So that's this, I guess, that's the last theorem for today, definitely. So lambda L is a one-dimensional cube. It's an interval of L adjacent sites in the discrete lattice. And then we have a small coupling result, namely there is a maximal coupling constant. So whenever V is smaller than the maximal coupling constant, and the Fermi energy is critical, one of those two energies I just explained to you. Then the expectation of the entanglement entropy, we're in one dimension, so the surface is of order L to the 0 multiplied by the logarithm, has a strictly positive limit. So this means that the growth of the averaged entanglement entropy is at least an enhanced area law in this one-dimensional model, despite the fact that the spectrum of the Hamiltonian we are looking at is entirely pure point with exponentially decaying eigenfunctions. The point is that it is dynamical localization which breaks down at these critical energies 0 and V in the spectrum. And this is this breakdown of dynamical localization. This gave rise to the T/3/2 growth of the second moment. So that's in a way the answer to how strong must localization be in order to prevent an enhancement. Well, it has, at least from what we can say here, it has to be at least as good. It has to be dynamically localized. Just spectral localization with still exponentially decaying eigenfunctions alone is not enough. Okay. That's in a way the news here. Of course, you can go away with your Fermi energy from these two critical points. So whenever you look at a Fermi energy that is in the spectrum, but not a critical point, so then one is in the localized part, then this statement for the area law of localized, Anderson localized system that are by Pastur, Slavin, Elgart, Schabina, Pastur, that I showed to you before, still applies, and you get an area law, which in one dimension means constant. So there is a clear distinction whether the Fermi energy is at one of these two critical energies, where you see an enhanced area law, and whether you are away and you get an area law.
Mm-hmm.
It's not, sorry.
Just a stupid question again. Now, suppose one takes eigenvalues which are close to this critical value, then the corresponding eigenfunctions do the decay slower and slower?
Yes. I mean, the spectrum, exactly, Felix. The spectrum is still a dense pure point spectrum. The spectrum is still a dense pure point spectrum. So you have eigenvalues sitting arbitrarily close to your critical energy. But each of these eigenfunctions decays exponentially, but the growth is slower and the decay is slower and slower the closer you get to the critical energy.
I see. If you go right to the critical energy, then is there still something like an whatever? There's
it's not. You see, I mean,
this eigenfunction, but it's no longer an L2 or something like that.
No, you cannot say this. You see, the point. The thing is, the spectrum is a closed set. That's general spectral theoretic blah blah. The spectrum is a closed set, but we are in a separable Hilbert space. In a separable Hilbert space, you can only have a countable number of eigenvalues. So even when the spectrum is pure point and it fills an interval, it has to be dense, because that's the only way how you can make an interval out of a countable number of points. You see? Mm-hmm. And that's one thing. The spectrum, the closure of the set of eigenvalues, is non-random. However, and that now comes to the heart of your question, the set of eigenvalues itself is highly random. So when you change from one realization of your random variables to another, your eigenvalues change like crazy. It's just that their closure always remains the same.
I see, okay. Mm-hmm.
So having said this, I answer your question with a I don't know, because I do not even know whether this critical value corresponds to an eigenfunction, to an eigenvalue. In fact, what I know is with probability 1, it does not correspond to an eigenvalue.
Mm-hmm. I see.
I mean, there's a general theorem. Given a specific energy in the spectrum, this coincides with an eigenvalue with probability 0. So from that, yeah. So you do not know what happens really at this critical energy itself, except that you know that when you approach this critical value, all the localization lengths they grow and get bigger and bigger, and the decay gets worse and worse.
Okay, thanks.
Good. So in order to, I'm already 6 minutes over time, I see.
Well, don't worry. I mean, we have enough time. So we have 1.5 hours anyhow, so don't worry.
So I have two, I think one thing I would like to say, I would like to add, and I think would be a good thing to close, because I have prepared some strategy of the proof for the stability result. I mean, if you want to see it, you have to say, because this is what I would. These are 3 transparencies, but this I would have skipped, because I think I wanted to keep it an overview talk. But let me rather end with a conjecture. That's because this is something people have tried for almost 8 years now. Looks simple. Everybody turned away being frustrated. So conjecture. We are in D space dimension, no particular dimension. D is a natural number. H is a reasonable Schrödinger operator. H minus Laplace plus V, a reasonable Schrödinger operator. Which means I suppose it's bounded below, for example. That's one part of being reasonable. E.g. bounded below. Let EF be a real number. Well, it's only interesting if it's in the spectrum, otherwise it's boring. Let EF be a real number, the Fermi energy, then show that the worst thing that can happen is an enhanced area law. So lim sup L to infinity SEF of the scaled volume lambda L times lambda, and of course lambda is also nice. Think of lambda cube, divided by L to the D minus 1 times logarithm L. This is finite.
But now you don't assume any decay assumption on the potential.
No.
Because I guess like if the potential is compactly supported, then one can...
Well, for compactly supported, I mean, we know it's an, well, if it's compactly supported, we have the bound.
Exactly. But for example, if you take Coulomb potential, it's already unknown.
It's unknown. It's also unknown if you take, if we take a periodic potential in one dimension plus a compactly supported potential, because we cannot do, I mean, I didn't show you the proof. We cannot perturb around the periodic potential. We can only perturb around the free operator.
And what about like a rapidly decaying potential or Yukawa potential, something like this?
We are currently, I have compactly supported simplifies, the compact support simplifies things a lot. I believe that sufficiently fast decay in infinity is also sufficient. I'm convinced, but this is something we're trying at the moment. So that's one point of generalization that we're looking at. But I believe it's true.
I see, but already whatever rapid decay is already not so easy apparently.
So with this, I think that's in a way a good point to end the talk and to answer other questions or remarks on your side. Thank you very much.
First of all, Peter, thank you very much for this beautiful talk. And then let's open the discussion. I mean, if you want to ask something, just go ahead, unmute yourself. Well, maybe then I just ask the question just to start the discussion. So now, what is the difficulty in proving it, for example, for rapid decay? Of course, we haven't gone through the slides where you explain your proof. Of course, I mean, I would also be interested in seeing a little bit how the proof goes, and then at the same time, now what happens if you don't?
Okay.
If it's not compactly supported, what goes wrong?
Yeah. Let me flash part of the transparencies where I have the strategy of the proof. It's not necessary to understand the details, just some certain key points. So this is the entanglement entropy, okay? And this is this function h that I made a drawing of. The first step is that we bound this function, we bound this function from below and from above by something simpler. Simpler in terms that this will allow us to apply later the triangle inequality to do the perturbation. Okay, so.
And simpler also means smooth, I guess. I mean, smooth at the two endpoints.
This is smooth. This is less smooth. Let me. So I would have done that. So the lower bound, this is this parabola. It's really adapted. So that's a parabola here. Well, of course, it's the parabola is only. Well, I cannot draw it well. I continue here just to make clear that the slope at 0 and at 1 is finite. Now that's what you said. It's totally smooth. We're only interested in the interval from 0 to 1. So the parabola is as smooth as it can be. The other function has an algebraic singularity in the derivative. It grows out even more.
I see, so like a square root. So that's
yes, like a square root. And then again, it goes up here. And this is the upper bound. This is so excuse my my drawing, but you can see what I want to say.
Sure.
Okay. So that's the smooth lower bound and that's the upper bound. But I don't care about this algebraic non-smoothness. All I'm interested later then is having a function to which I can apply the triangle inequality. Okay, so you see here and there we have the combination lambda times 1 minus lambda. Okay, the operator, I mean, lambda is what goes into the function h. So this is the operator that goes into the function h. So I look at this operator times 1 minus this operator. Okay, you massage this a little bit and you can see that this operator that is then relevant here can be written as a mod squared of an operator I call QL. And this QL is, again, the Fermi projection as before, the scales, the indicator function of the scale volume. And here I have the indicator function of the complement of the scale. Okay. It's just using properties of projections. It's utterly trivial. But we do not want to do it now. Okay, since this is a mod square, here, and I have to take the trace of this function here, I mean, then trace of this function, which is this operator, this gives me here a Hilbert-Schmidt norm. This trace of this mod squared operator gives me the Hilbert-Schmidt norm of this QL. So that's Hilbert-Schmidt. On the other hand, here I have an addition, an S, a power S. So with this 2 here, this gives me the 2S Schatten von Neumann-Schatten norm of the same operator, QL. And now I said that this now I can do perturbations. I write, I mean, so this is QL refers to the perturbation. QL0 refers to the Laplacian. That's the same thing, except that H is replaced by the Laplacian. Now I use the triangle inequality. I write either the Hilbert-Schmidt norm or the 2S Schatten norm of QL is bounded above by the one of QL0 plus the norm of the difference. Okay, and I do this on the left-hand side and on the right-hand side, either with the Hilbert-Schmidt norm or with the 2S Schatten norm. I choose S large enough so that it is really a norm, so that 2S is larger than 1. And you have this bounds from above and below for the entanglement entropy. Now these terms are going to be my leading terms, and these terms are going to be my error terms.
I see.
So these two terms will make up the enhanced area law as far as the growth in L is concerned. And these two terms, my claim, grow slower in L than the enhanced area law. Okay, and the heart of the matter, I mean, that's really where one has to work, is we use the limiting absorption principle to make sure that the Hilbert-Schmidt norm of this difference here, this Hilbert-Schmidt norm, is uniformly bounded in L. So the super over L is fine. That's the point.
I see.
And then with this, one can forget more or less the rest. So I have repeated these two steps from the previous transparencies. Having this bound on the Hilbert-Schmidt norm, I get a bound on the 2S Schatten norm. That's not, but that's not the point here. Just believe me. As soon as one can argue that these two terms are the ones that make up the enhanced area law. So L to the d minus 1 times logarithm, and I claim these two grow slower. And in particular, this term here doesn't grow at all. Okay, so coming back to your question, I mean, where does this come from? And that's in a way the end of the argument, or also the core of the argument. I write down again what is this difference, QL and QL0. So this here, this is QL, and this is QL0. Oops, sorry. And this is QL0. That's just the definition. And here I have the difference of these two spectral projections. Okay, what I do now is I cover this region by unit cubes, and I cover this region by unit cubes. So I call the unit cube gamma n. So in the end, I will only be interested in these types of this, in such a type of expression. And then I have to make sure that, because in the end, you see, I'm interested in the Hilbert-Schmidt norm, I have to make this square summable in n and in square summable in n and square summable in m, because this gives a finite Hilbert-Schmidt norm, independent of what then this and that is. So I want square summability in m and in n.
I see. And then you need kind of exponential decay of the resolvent or something like that in order
Exactly. So the first thing is well, rewrite this Fermi projection as what is sometimes called a Ries projection. You use the residue theorem to rewrite it in terms of the resolvent for the perturbed part, for the unperturbed part. Good. There are already things hidden in there, because the contour here crosses, this is the Fermi energy EF here, so this is the Z plane. The Fermi energy, the contour here crosses the spectrum. I mean, the spectrum is from 0 and the Fermi energy is positive. So one has to make sure there's already one issue, that this is well defined, but believe me, it is. By the way, we already use the limiting absorption principle to show that this Bochner integral here is well defined. But okay, then also natural thing, use the resolvent identity twice to rewrite this difference of resolvents. And then I have one term that involves only the free resolvent, and one term where the perturbed resolvent is sandwiched from the potential. Now the good thing is, if the potential has compact support. Potential has compact support. And I know that the free resolvent decays, has a nice decay. I mean, it's explicitly known. You can write down an integral kernel and things like so. And we use the explicit decay of the free resolvent. I mean, there are also bounds on the decay from more general principles. They are not good enough. We really use the explicit representation of the resolvent. Bad. With this, so there is decay from the compact support here to the gamma n there.
Mm-hmm.
And on the other side, from the decay here, the compact support here to the gamma m there.
Mm-hmm. I see.
And the decay is just it's just good enough to get square summability in n and m. When you look at the Hilbert-Schmidt norms of this expression.
I see. So there's the potential, like it's not completely supported, even if it decays rapidly. This is not good enough because then you can no longer sum here. And
so the thing is, yeah, exactly. So if this, now what we are trying to do is when this is not compactly supported, we try an inductive argument by approximating it by sequences of compactly supported potentials, and then showing that the convergence of these approximants is fast enough so that everything can be put together. That's what we try right now. Okay, and since I show you, since you get to see this transparency, and I told you that the decay here is just good enough to get then the finiteness of the Hilbert-Schmidt norm here. And this means that you cannot allow for any kind of singularity coming from the perturbed resolvent. Cannot allow for it. Mm-hmm. But there is this bad part of the integration contour, which crosses the spectrum where the resolvent explodes. Mm-hmm. And this is where the limiting absorption principle comes in. The limiting absorption principle, I mean, it holds for a much wider class than compactly supported potentials. It's not the limiting absorption principle where the restriction comes from, but in particular, it holds for compactly supported potentials. And the limiting absorption principle asserts that the operator norm of this combination here, X is the position operator, that this operator norm can be bounded uniformly in where we are on this bad part of the contour, no matter how close to the spectrum. And since there's no point in having these, this is where usually these limiting absorption principles are derived in scaled Hilbert spaces where the measure is modified. So this is where these functions come from. But since the potential V has compact support, this is what you can accommodate in here without any problem. Mm-hmm. So, but the essence of the argument is there is no singularity allowed from the perturbed resolvent, and this is why one has to be particularly careful here where this part of the contour crosses the spectrum. And this is what it does.
Okay, so
that's in a nutshell. That's in a nutshell the idea what's behind the proof.
Okay, thanks. So let me just see, are there other questions? Well, maybe I have another naive question. I mean, now what you did was all for the Schrödinger equation. Suppose one would like to do something similar for relativistic equations, say Klein-Gordon or Dirac. Again, a static system, so static potential or no potential at all. Do you think that your methods could also be applied?
Well, I mean, the methods we have are for proving stability. So suppose you do have a certain behavior, say for the for the free Klein-Gordon or for the free Dirac equation,
Yes.
and then you want to perturb it by a potential, as long as you have resolvent estimates as the ones I just showed to you, that's what makes it work.
Okay, I see. But of course, the first step is to really compute it for the free Fermi gas.
Exactly. And I do not know. I do not know of any results.
In fact, this is concerning the free Fermi gas. Also asked Wolfgang Spitzer. Also, he told me that there are no results.
Yeah.
Which is like good news for us, because this is a bit the problem which we are looking at right now.
I see. I see.
But of course, then adding a potential would be the next step. So maybe it's a bit too early to even say.
Yeah. No. I mean, in a way, this would mean having a replacement for the Ségué type asymptotics for relativistic operators.
Yes.
So where the Wiener-Hopf operator is in a way suitably truncated, I don't know, in space-time. Well, why not? In space-time, a suitably truncated operator in space-time.
Yes, well, I mean, we would also consider Cauchy's surface, so everything would take place just in space. And the complication for Dirac is, of course, it's unbounded. The Hamiltonian is unbounded from below.
Yeah.
So you have to introduce like a spectral cutoff for negative energy.
Yeah, that's reasonable. Otherwise,
yeah, sure.
Yeah.
Well, and then at least superficially, it looks similar to the Schrödinger setting, but well, we are not. It's not so clear whether there will be some problems coming up.
It's not. I mean, the whole method of this proving these Ségué asymptotics. It's delicate. And I mean, this is also the reason why. I mean, in the non-relativistic, in these non-relativistic situations that I showed to you, one only knows about certain examples of certain small classes of operators where one can say something, but what is lacking is, in a way, kind of a general theory or more general criteria that allow you to deduce a certain behavior of these entanglement entropies or related functions. That's I mean, it's surprisingly intricate.
I see.
Yeah, yes, it would be nicer to have some. It would be nicer to have some more general approach. But as I showed to you with this, even with this conjecture, I mean this is kind of a general statement one would like to have.
Yes. So sure, of course, at first it doesn't look.
No, all I can nice to have.
Okay, yeah, sounds good. So it means one has to jump into the details and check it out, and then hopefully one can do something. So let's see.
Yeah.
Well, are there further questions? Well, apparently not. Well, then let me
thank you for your attention
once again for this nice talk. Thanks a lot.
Thank you.
And then I wish you all a nice weekend. And of course, then we'll see each other again next Thursday at our seminar. Okay, and thanks a lot, Peter, for giving the talk. I mean, for taking the effort to preparing all this and so on. So thank you very much.
Yeah, no, my pleasure. It was actually, I mean, I tried to avoid anything. So far, it was my first talk using with Zoom. I mean, except for informal stuff where I didn't care so much.
Oh, very nice. Okay, good. Well then, see you.
Okay, thank you.
Bye-bye.
Bye-bye to you all.
Bye.
Bye-bye.
Thank you. Bye.
Bye.
Thank you very much. Lots of good stuff.
Thanks. Bye-bye.
Thanks.